Am I audible? Yeah. So most of the time we go for design verification. It's a continuous process so that we are able to sort it out all the design rules. We are able to follow all the design rules so that there might not be any fabrication defects coming into picture after the fabrication. And because of this explicit testing, what is the basic reason of this all this explicit testing? This is all because of the masking problem. Suppose you have a mask, and in this that mask, we generally do all this processing in a clean room. But yes, the clean room is also defined in terms of a number of dust particles. You cannot completely remove the whole dust particles. There may be, suppose you wanted to make these two lines, and that is why for making these two lines, you have made a mask. But because on this mask, there may be a dust particle is there. Okay. So whenever you are going to transfer the pattern, how it seems to be, this seems to be like this. Okay. What is the problem? You wanted to make these two separate lines, but because of this dust particle, your pattern will not be transferred correctly, and that is why you are getting some bridging fault. Okay. So there may be a certain faults are there, and that all these faults you will see over there. Masking problem, lithographic problem. Most of the defects are arising from this masking problem. There are some certain problems are also there. We cannot say, like you have already seen about, whenever you will discuss about, you taught teach about, learn about the VLSI fabrications. So you have seen that if the crystal will distort, if you are doing some ion implantation, then the crystal property will deteriorate. This is also a kind of a defect. But whether these defects will lead to a failure, will IC failure or a functionality, it will hamper the functionality? No. Okay. Yes, it will deteriorate the functionality. It will deteriorate your performance parameter, but it will not hamper your functionality. There is a two things, guys. There is a two things. Some defects are there, but not all defects are bad for us. That is why I have already told you there are some certain defects are there, and you cannot make any kind of a device, any kind of an IC which is completely defect free. Always there is a defects. Okay? But not all defects will give you a wrong functionality. My main aim is to find the wrong functionality or circuit which gives you a faulty result or a wrong result. Okay? So there are so many defects are there, but we are not concerning about it. That is why I have written over there. These mask problem, lithography problem, these are some of the issues. Starting from the wafer fabrication, we have encountered many defects are there. Crystal defects are there. Artifacts will be our crystal structure of wafer is damaged, and so many defects are there. Out diffusion, all these things are there. But the problem is that we are mainly concerning about all these defects that will actually hamper my functionality. Okay. There are some implicit testing are there. Why this implicit testing? We cannot test it out. There are some electromagnetic interference are there, some alpha particles are there. What is this alpha particles are there? After the fabrication, although you have already checked it within the explicit testing, you have checked your functionality will, you are getting the good functionality, your IC is a good one. But if you send it to some CHE or some in aircrafts, what will happen because of some radiation effect? It will the functionality will hamper. So it is in my hand? No, and we cannot check it. We cannot check it. So these are the some implicit testings are there. So that is why most of our focus is to just to check the explicit testing. There are some certain testings are there, like reliability testing, electromigration problem is there. Most of these problems are related to the metal. Corrosion problem is there. So all these things that we have to check. So these are the different kind of a test. Are we have to do all this testing? Yes, most of the testing we have to do. Okay. So this is the in detail version. We will discuss it later on one by one. Okay. So there are some certain tests are there. As I already told you, then wafer test setups are there. What in this case you will see, this is an automatic test equipment. What you are going to do, it is a completely automatic system. You just have to put your wafer, and you are easily get whether it will check depending upon some functionality whether which die is actually correct or not. Okay. So it will simply check like in this way. You can see this green portions have passed all these tests. All these parts have checks, but some of the fail have these are some functional tests are there. Okay? This red portions are there. There may be many reasons for the faults because different faults are there. Okay? It is not true. Maybe a single line will stuck to 1. Maybe a single line will stuck to 0. Maybe some open faults are there. Maybe some short circuit faults are there. Some delay faults are there. What is the meaning? Every fault that we have discussed it later. Okay? So there may be a number of faults, but the problem is that you don't know anything then that which fault is there and at which point these faults are there. So how can you repair it? So first of all, you have to identify which faults are there. It is kind of a random pattern generation. You are randomly, you don't know whether some faults are there or not, and you don't have to do. No, I will definitely find some faults are there. Okay. So all the time your main aim is to try apply some certain input combination that we generally use for whenever we go for the or a customer will generally apply all these input combinations that and then find whether for all this combination whether we are able to identify some faults or not. Okay. It is my meaning. There may be several faults are there. Okay. So why we are going to invest in testing? We have already seen that this is the cost per test. If we implement this IC on a board, then it will cost 10 times. Actually, it seems to be a 10-time rule. That is why I have written over there the rule of 10. It is given by the Davis in 1982. And if the board is in the system test, if it is up to the system level and you wanted to check the system, then it will cost more to you. Okay, that is why it is advisable that each and every point you will check. Okay? Like as I will discuss about it, that ultimately our prime, you can say, suppose I'm making some module or some ADCs over there. What is it? How we can make an ADC? How we can make an ADC? So there are some transistors are there, some resistors are there. So ultimately, we have to check all these transistor and resistors are. Okay. So it will cost the testing cost for finding this faults in transistors and resistance is quite easy. While it will be a very cost or you can say it very expensive process to find all the defects in the ADC. That is why we are saying that you first have to find the ACC at testing at the basic level, and then you go for the. And this is the case I have already discussed to you that ultimately you have to ensure between the quality and the economics. If you go for more test, then your test cost will increase. Definitely you are getting the high test quality ICs. But if you are reducing the number of tests, then your test quality will be poor. But yes, the repair cost will be less. You have to pay more repair cost if a customer found all these things. So that is why ultimately there is an optimization. You cannot afford to check for all combinations, and you cannot uh, uh, do for all the repairing purpose. So that is why ultimately how we can reduce the cost up to a certain level for some number of inputs, less number of input. Your main aim is to finding less number of input so that you are able to get it up. Okay. So can I take more 10 to 15 more minutes so that I will able to explain what faults are there?
Yes, sir. Yes, sir.
So these actually how we can sort it out. So there are two different mechanisms. Suppose you wanted to find a fault. Actually, my main aim is to find the fault. Okay, and then going for the diagnosis. Then how you can find a fault? First of all, there are two mechanisms out there. Whether I'm manually checking all these faults, like suppose I have a gate over there, and first of all, I have to know that what kind of different fault it has. Okay, let it be my manager says you have to apply only two test patterns. I know that it is actually a two input gate. And if it is a two input gate, there are four different input combinations. But my manager says, no, you don't have to apply for the four inputs. You have only permitted to apply two input vector, two test patterns, so that you are able to get the maximum fault coverage. Okay. So on what basis I am able to find this? Which two inputs I have to apply? Is it either 0, 0, 0, 1, 1, 0, 1, 1. And how we can sort it out? How we can sort it out? We have to find, we have to check what we have to find what kind, what we have to find what processes we have. So first of all, we have to understand what fault to test. Okay. Then how the test patterns are obtained. Okay. What is the test quality measure? How is the test quality measure? What is the fault simulation? And whether we are able to, how the test vectors are applied and the results are evaluated. So these are the basic scenario that we have to check. And as already told you, this is the basic part. This is the defect. And what the defect is, unintended physical difference between hardware implementation and its intended design. This is just a defect. And defects can be anything. Defects can be anything. It's a crystal orientation defect. It's a doping dependency defect, doping profile defects. There are so many defects are there, but we don't concern about all these defects. These some of the defects, or you can say some of the defects only will deteriorate my performance. Okay, like if you are taking an example of an orientation, suppose in general, I think most of you know that for making an any surface device or a MOS devices, we generally prefer 100 orientation. But if you are getting 111 orientation, then what it harms? It will just reduce my overall current, or if specifically I have to say, say the surface effects will be less in this case, 111 orientation. Sorry, more in this case, 111 orientation. So that will give me a lower threshold voltage. Okay. So these are the defects, but we cannot do all the for these defects. Ultimately, defects will lead to some faults. And what the fault is? Representation of a defects at an abstracted logical level, like this way. This is kind of a defects we are talking about. Okay. And then whatever be the fault, that will lead to error, and error will lead to failure. So so that you have to ensure the circuit will not be, your IC will not be going to fail. So that is why you have to reduce the fault. Okay. And there are these different type of faults we have. These are some real different faults are there. Passing fault, but what these faults are: missing contact window, parasitic transistors are there, like lights up, you have heard about it. Oxide breakdown. Okay. Some of the defects are related to the material, like bulk defects, crystal imperfections, ion migration. As I already told you, these defects are not important for me. This is just deteriorate the performance. It is not hampering the functionality. Okay. Time dependent failures are there, dielectric breakdowns, electromigration, packaging failure, contact degradation, seal leaks. These are the different kind of failure. But we have to categorize in terms which will actually impact the fault. We are not concerning about all the defects. We are concerning about the fault. Okay. So that is why the defects can be broadly categorized into two bars. The random defects are there and the systematic defects are there. Random defects which are independent of design and process. Okay. These are the random defects. And systematic defect which depends on your design and processes used for the manufacturing. Which processes, which manufacturing process, which line you are using for fabrication. So this will actually have systematic defects. Okay. So these all are the examples of defects. All defects, dust particles. This as I already told you, because of the dust particles, your transistor may be completely open or it is completely short. Okay. That means if either it will give you a zero value or it will give you only a one value, always it is sorted. Okay. So this is the way that there are such certain changes are there, and that will lead to the functionality. Okay. So these are the different ranges. Like here you can see, you wanted to create a line, but because of some issue or the process defects, there the line is not completely fit. It is kind of an open. So whatever be the potential here, it will not pass to this part. Okay. Actually, you may say that yes, because of the capaciting coupling, there may be some of the charges will move in this way. Yes, but ultimately, if it is a logic one, then you are not getting logic one here. You will getting some high impedance value, and that high impedance value may be of 2 volt, maybe of 3 volt if you are using the 5 volt supply. Okay. So that would be any case. So ultimately, this may lead to whether it's a logic 0 or logic 1. So this will be the case that we have to take off. So these are the random defects. Random defects because of the nature. You wanted to create this kind of a structure, and because of the dust particle, these two lines are actually shorted. So this is random. I cannot comment on this part. This is all because of the dust particles. Okay? But these are the systematic defects. Systematic defects because of some process, because of some fabrication that we are using. Like in case of a masking, you know that it is not a feasible approach to perfectly make this kind of a layer. Ultimately, it's a fabrication process. So this lithography seems to be like this. And because of this fabrication process, there may be a chance that it will short. This is kind of a systematic defects we have. Okay? Random defects, we cannot do anything about it. There should be there, we cannot do it. Okay? So why fault model? Fault model quantify the test quality. Defects are hard to handle. How many possible defects in a circuitry? There are too many defects are there. But ultimately, we have to find the number of fault that can be easily calculated in the circuitry. Okay? So this is the task that we have to perform. Okay? So how we can do so? This is all because of this case, like test pattern and test sets. What the test pattern? As I already told you, this is a circuitry. This is a circuitry, and suppose there is a fault. There is an stuck at zero fault. Sorry. Stuck at zero fault means always this is at zero. How you can find it? You just have to apply some certain set of input so that you are able to get the output. Okay. If I'm applying 1 over here, then ethically my output, the correct output should be 1. But yes, because of this stuck at fault, I'm able to get 0 here. So that is why, because of this combination, I'm able to find it. While all the other combinations are able to find all this fault stuck at 0 fault. No, 1 0. Your correct output is also 0. Your main output is also, this faulty output is also 0. So for all the different combination, whether it's a 0 0 0 1 or 1 0, you are not able to find this fault. Only 1 1 combinations will be allowed you to find this fault. Okay, so this would be the basic case. Okay, so we have to ensure that which test vector, but as I already told you, we are not going to apply everything. So that is why manual approach, automatic approach, both are important to me. Manual approach, automatic approach will not give an intelligent approach. Okay, automatic approach, there are some certain patterns are there. It will randomly apply. But as I like in this case, we can easily find out if it is a stuck at 0 fault. We can easily apply our mind. Yes, it can be easily detectable by 1 1. Okay? So this is the case. Okay? How test length means how many number of test vector you are going to apply for finding this course. Shorter the test length, lower will be the test cost. Okay? So always you have to find less number of test vector so that you can identify your this test fault and you can diagnose them. So this is the all how we can define it based on the fault coverage. Okay. This is the fault coverage, number of detected fault upon the total number of faults. Okay. That percentage. If your IC has 0 to 70% fault coverage, it is not good. That is why I told you that 70 to 90% fault, if you are able to detect, that is sometimes acceptable. And actually, it actually depends the standard of a company. If a renowned company is there, it's more rely on finding more test vectors so that it will able to find more number of faults. So that is why the quality will increase. Definitely they have to pay, and this is one of the reason that a standard company like I'm not going to name any company, but in case of any standard company, you will say their product is costly, much costlier than the this case. Like if I'll just take an example. I'm not saying that another way. Like if you are using an AMD processor and you are using an Intel processor, definitely Intel will put more effort as compared to the AMD, and that is why it will cost more to you. Okay? Like AMD, they are making that processor, but they are not actually checking all this. So most of the costing will come in from the testing side as well. So if you want a higher quality, then you have to pay more for that. Okay? Because higher quality, most for fault coverage. Now I'll directly come to the classification of faults. So what these fault models are? Fault models are nothing. Actually, these are some of the faults these are some of the models so that it will able to detect some certain errors in a circuitry. Okay. So there are some certain errors are there, like there are some logic circuitry, so many errors are there, like some gate level errors are there, transistor level errors are there. Gate level stuck at fault. Stuck at means, as I already told you, I'll just come into the direct part. Okay, what the stucket fault is? Stucket fault means like any of your, if you closely look about this node, it is always stuck at one. It is always stuck in one. Whatever with you, whatever with the potential, whatever with the input you are going to apply. Suppose I'm going to apply 0 AM. So depending upon, I'm expected that as the output will be based on this 0, but it will always be 1. And why it is so? Why it is so? Because ultimately, why it is stuck at 1? Because anyhow, this will relate to the supply voltage. This is supply related to the supply voltage. So whatever be the potential that you are applying, it doesn't make any changes in this one. So always, then how you are going to detect it? This is the main issue. How we are going to detect it? Similarly, any of the wire may have stuck at 1. We are generally writing this way, stuck at 1. Some in some books you will find at this way, stuck at 1. Some are writing in a complete way, stuck at 1. These are some notations are there. Okay, so these are some notations are there. So one are there in any wire, there may be a chance that it is either stuck at 1 or it is stuck at 0, and the other possibilities are it is completely fault free. These two are the faults, either it is 1 or 0. Okay, so we have to check each and individual lines. Okay, like this, there is a circuitry. There is a circuitry. You will see it is a very short circuitry. Okay. Very, it is not it is a very easy circuitry, but you will see there are some lines are there, some input lines are there. Although 4 input lines are there, each line, as I already told you, each wire have a possibility of 2 faults. There may be a stuck at 0. There may be a stuck at 1. Okay, so each and how many lines are there? 1, 2, 3, 4, 5, 6, 7, 8. So total 16 fault probability we have to check it. Okay. Are you getting it? So there are 16 different stuck fault. And stuck fault are the major component of the finding the faults, because most of the faults are covering this way only. Okay. There may be a single stuck fault. There may be a multiple stuck fault. Okay. Like in this case, if you will see there are different lines are there. And one more thing I just wanted to clear it to you. You can see this is the stem and this will be the branch, but stem and branches are counted separately. Whenever you are going to find, suppose I'm giving you a question that you just have to find how many number of lines, how many single stuck fault possibles are there. You just have to find all these numbers: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The total 24 possibilities are there. Although we will see that G will be changed to H. Yes, G is changed to H and G is going to I. But there is a chances whether the metal is broken from here or the metal is broken from here or it is from here. Okay. So there are several stuck faults are there. And most of the time we are mainly concerned about the stuck fault. Okay. So this is a gate level approach. In this case, you will see there are single stuck fault. As I already told you in earlier cases, like I have given you an example that total 6 different faults are there. If you are taking this example, this is a only a one gate single and gate is sorry and gate is here and gate is here. There is an A input, B input, and C output. So these 3 lines are there. So how many stuck fault are possible? Single stuck fault are possible 6. See, so how can we find it? We just have to apply some certain number. If we are applying 0 0 over here, what will be there? It will check whether it's an 0 0. It will check only the stuck at 1 at C. Okay. So only this fault it will take. So if in earlier cases, if I told you that you have to check only 2 combinations. In earlier cases, I am giving you a question. Your manager will told you that only 2 combinations you can pick. Then which combination you can pick? Are you getting these 2 combinations or these 2 out of these 4 combinations? Because if you are using all these 4 combination, you are getting 100% fault coverage. But if you want to choose any 2 combination, then how can I pick these 2 cases so that I can get the maximum fault coverage? Now you will see. If I'm choosing 0 1 1 1, you can see 1 2 3 4 5, or total 5 fault I can cover. And what are the how many total faults are there? Total fault will be 6. So 5 out of 6. So I will definitely prefer 0 1 and 1 1 option for that. Yes, if anyone told me that you how many number of test case you can use so that you can find the complete whole coverage. I'm not going to apply whole these 4 cases. I can go only for these 3 because you know that on these 3 combinations I will be able to find all the faults, 6 out of 6. Okay. So this is the basic case of a stuckered fault. Okay. There are some multiple stuckered faults are there, but in general, I just wanted to tell you, we are not going to find the multiple stuckered fault. What the meaning of multiple stuckered fault? Multiple stuckered fault means there may be a fault present in this line. It may be a stuckered 1, a stuckered 0, or maybe a fault free. So there are multiple stuckered faults, but the problem is that multiple stuckered faults are too many. We are not able to find it. Okay? Like as I already told you, if you are going to find the single stuckered fault, then there are total 2 n combinations are there. If n is the number of line, if n is the number of line, then only 2 n combinations are there. But if you are going to find the multiple stuckered fault, there are 3 to the power n minus 1 combinations there. Why 3 to the power n? 3. Why 3? Because we have in each line we have 3 different kind of a fault. There may be a stuckered fault, there may be stuckered 1, stuckered 0, or maybe a fault free. So in all the lines, how many total number of, suppose n lines we have, so there are total 3 to the power n combinations are there. And definitely any one combination is there which is completely fault free. That is why we have minuses. So how many total faults are there? To the power n minus 1. And that is why most of the time we are not going to consider the multiple stuckered fault. Actually, a single stuckered fault can detect many multiple stuckered fault, and this is the proof of that one. Hughes in 1986 will do all this experiment and find out that they are putting different sets, 16 sets they have taken, and this is the test length. These are the test length, and it find that how based on the single stuckered fault, and they are going to find out how many multiple stuckered fault we are able to find based on only single stuckered. You can see there are 79,600 double stuckered faults are there. Okay. So what they will do, they are just applying single stuckered fault model, and you will see that in test pattern, out of this 12 length, 9 there are 9 undetectable double faults are there. And when you in some of the logic, you will see there are no such multiple stuckered faults are undetected. All the stuckered faults are detected only by the single stuckered fault, and that is why the single stuckered fault is kind of a better approach. It's a feasible approach. And that is why we go for the single. There are some certain logics are there. Logics are arranged in that manner. Like in this case, if I'm taking this case, you will see, let it be, I'm applying some logical inputs are there, and you will see there are no such faults are detected. While in this case, I'm applying some, there isn't some certain F1 fault is there. And you will see, if you are, if stuck at one fault is there, you will see their output is completely different. Depending upon, I'm applying only these inputs, and you will see your output is completely dependent, able to find and detect, able to find the fault. How this is the correct one, and this one is the faulty one. So whenever you are you have a correct one and you have a different faulty one, different output, that is, it's the any of the circuitry will be fault. Okay? So this is the case. But similarly, I'm able to find single stuckered fault here also. But if I'm going to incorporate both the faults in this circuitry, you will see there are some certain faults are there. But are we able to find it? No. So many of the double stuckered fault are not able to find if we are incorporating the circuitry in that way. If we are incorporating most of the circuitry, most of the time we are going to make a tree-like structure. And because of that structure, we are not able to find certain faults. Okay. This is called as the fault masking. We have to do some certain remedies for making this fault masking. Now, the another thing is that bridging fault. As I already told you, what the bridging fault is. Bridging fault is when X1 and X2 will become short. How we come short, we have already seen, either because of the dust particles or because of the masking issues. So this is known as the bridging fault. Ethically, X1 and X2 are two separated inputs, but the problem is that internally, because of the fault, they are going to bridge it. Okay, there may be a chance, this is called as the input bridging, and there may be a chance that the output is bridging with the input, and it will, you will see there is a feedback path. And because of this feedback path, it will actually hold the data. Seems to be a memory. Okay? So there may be a very severe situations. Okay? These are the bridging faults. Similarly, there are some other faults are also there. I'm just coming into the, yes, stuck it up and stuck it on. Okay. What these faults are there? Suppose I'm taking this kind of a CMOS circuitry. Which circuitry is this one? You can see easily visualize. This is nothing but actually an AND gate. Two input AND gate. Okay. Suppose my this A transistor will always be stuck open. What is the meaning of stuck open? Stuck open means it will not pass any value. It is connected to 1, but it will not pass this value to C or this node. It is completely open. Okay. So how we can find it? If you are applying some certain input, you can see if I'm applying 0, 0 over there, what will be the outcome? What will be the outcome? Outcome seems to be 1. Are we able to find out it? Yes, in this case, we are able to find out it. But if I'm applying 1, 0 over here, are we able to find out it? No. Okay. Because at 1, 0, it seems to be the 0, 1. Okay. So this would be the case. There are some other faults are there. So if I'll get a chance later on, sorry, I don't know anything about whether the talk is of 1 hour. So I have prepared so many slides. So in case of any doubt, you can ask me. I'll stop it here. You might have some. Sorry, Teshna.
Thank you, sir. Thank you so much for your valuable information taken from you. Participants, if you have any queries, ask our speaker.
Sir, do students have any opportunity in this field, VLSI testing?
Yes, ma'am.
Any job
Yes,
opportunity?
yes, because in India, most of the work has been carried out only on the VLSI verification part. And if one would be interested in testing, they have to go and find approach towards the global foundries, ST Electronics, because they have their own fab labs and they can find. Still, there are so many things are going on, as you already mentioned, and most of the cost has been covered by the covered for the testing purpose. So we actually wanted to reduce the test vector or find effective test vector, so that less number of vectors we are able to find out all number of faults and get the maximum fault coverage. So there are several opportunities are there.
Thank you, sir. Thank you so much. I would like to say thank for IIC giving me this opportunity to organize this expert talk, which is helpful for all the students and faculty members. I must mention our deep sense of appreciation for all the participants for attending this session and for making it as grand success. All participants, the feedback is given in your chart. Please give your feedback in this feedback form. Thank you all. Thank you so much.
Thanks to all.
Thank you, sir.